Hello everyone, very good evening. I welcome you all at India's most comprehensive preparation platform for all competitive exams, that is BYJU'S Exam Prep. So guys, as you all know that this year IISc Bangalore is going to organize the GATE 2024 exam. So BYJU'S Exam Prep team has come up with a series in which we guys are going to discuss the questions from the previous year GATE papers, which in the years in which the GATE examination was organized by IISc Bangalore, that is from 2002, 2008 and 2016. So in this particular series or in this particular session, the very first part will be related to concept of computer organization and architecture. So I will discuss the questions of computer organization and architecture from two particular chapters in this particular session. One will be the basics of computer organization and architecture. Another will be the basic addressing mode, and control unit design and ALU and data path concept. So the basic questions related to those particular chapters. Okay, sir. So this is the brief introduction of myself. My name is Vishal Rautia. I have 10 plus years of teaching experience, and following are the achievements and areas of expertise. Okay, so there's an announcement that at 7:30 p.m. tonight, Abhinav Negi sir is going to conduct a workshop in which we will discuss 5 tips along with you, which are perfectly executable, and if you utilize those 5 tips, then you will be able to do good in your GATE 2024 exam. So this workshop is absolutely free. Do attend this particular workshop. Okay, so let's start with the particular session of computer organization and architecture. So please, so you all know that the most important topics of computer organization and architecture are: one is memory organization, another is instruction pipelining, and in the recent year, very frequently the questions are being asked from the topic of direct memory access, that is DMA. So these are the 3 most important topics. I'll discuss the questions of all these 3 topics in the tomorrow's session. For the today's session, it is the very first session in this particular series, so that you all will come to know about this particular series. Therefore, I am keeping the questions only from 2 topics, that is basics of computer organization and architecture and ALU control unit design. Okay, so let's look at this. A processor that has a carry flag, overflow flag and sign flag. So the basic concept, bit as a part of its program status word. So this is nothing but your flag register. So in your flag register, you are having the information of carry flag, overflow flag and sign flag. Perform the addition of the following 2's complement numbers. 2's complement number. So you all must know that this overflow flag is used on the system when we use signed arithmetic representation. In signed arithmetic representation, numbers are represented using 2's complement format. So after the execution of this addition operation, the status, after the addition of these 2 numbers, the status of carry flag, overflow flag and sign flag will be respectively. Please give me your answer. Please provide me with your answer. 0, 1, 0, 0, 1, 1, 0, 1. This is your first number. Another is 1, 1, 1, 0, 1, 0, 0, 1. So this is the very basic question from COA, which is asked in GATE 2002. So 1 plus 1, 0, 1 carry. Now 0 plus 0 plus 1 will be 1. 1 plus 0 will be 1. 1 plus 1 will be 0, 1 carry. Right? 0 plus 1 will be 1. 0 plus 1 will be 1. Now this is important. 1 plus 1 is 0. There is a carry. Right? Now 0 plus 1 is 1, and this 1 plus 1 will be 0, and there will be a carry. Okay, sir. Now Chandrayaan 3 landed. Yes, congratulations everybody. Congratulations. Okay, so what will be the answer? Sir, Carry flag, yes sir, carry flag is set. So the value of carry flag will be 1. So what happens with the overflow flag? When do we set the overflow flag? So there are conditions with respect to overflow flag, that if there is carry into MSB and no carry out of MSB, then carry flow will be set. Overflow flag will be set. Otherwise, if there is no carry into MSB but a carry out of MSB, then also carry overflow flag will be set. But if there is carry into MSB as well as carry out of MSB, or if there is no carry into MSB and no carry out of MSB, then in those two cases overflow flag will reset. So this time it will reset, that is the value of overflow is 0. Now, so what is the value of sign flag? The value of sign flag depends upon the most significant bit of the ALU output. So this is the result. This is the ALU output. You may say, sir, this one is part of this, but no, this one will be available in the carry flag or carry status bit. Therefore, it is not a part of output. You may have some other computation based on that. So the value will be 0 for sign flag because MSB is 0. So if MSB is 1, sign flag is set. If MSB is 0, sign flag is reset. So 100 is the correct output. So correct answer is option B. Let's look at the second question. Sir, this is very good if you try to analyze this. Assume that effective address equals to X. So first we are writing X plus. So what does it mean? Is the effective address is what? Is the effective address equal to the content of location X? Effective address is what? Sir, effective address is the content of location X with X incremented by 1 word length after effective address is calculated. So this is indirect. This is trying to represent indirect. So basically, what does it represent? Sir, X is not the effective address. X is a memory location. X is a memory location and content of that location is your effective address. And after calculating the effective address, you are incrementing the value of X. You are incrementing the value of X. Now, if you are saying minus of X, so please look at this. This plus is the post incrementation. What type of incrementation? So it is post incrementation. That is, first you will evaluate the effective address, then you will increment the value of X. But here this minus will represent it as pre-incrementation. Right? So what will be the effective address? So to calculate the effective address, first we will have to decrement the value of X and then we will have to access the content of that memory location. So this is the effective address equal to the content of location X with X decremented by 1 word length before the effective address is calculated. So first you need to decrement the value of X and then you need to access the content of location X to get the effective address. So this is post incrementation for effective address and this is pre-decrementation for effective address. Now, sir, if it is the situation X minus, then it is post decrement. That is, you will calculate the effective address based on the content of memory location X, and after calculating the effective address, you will decrement the value of X. So it is the effective address equal to the content of memory location X with X decremented by 1 word length after the effective address is calculated. Okay, sir. The format of instruction. So it defines the format of instruction. That format of instruction is nothing but it will have one opcode. Okay, then it will have the source, that from where you will get your data, and destination, that where actually you need to store that data. Okay, now which means that destination will be nothing but source operation with a destination and result will be stored at the destination. Okay, so this is just an opcode. So let's try to understand. If I write something like please first try to understand this, that this is nothing, the opcode 1. So whatever the first location will be your source and whatever the next location will be your destination. But how do we perform the operation? That, so whatever is present in the source location on that particular content will perform the operation with the location, corresponding to the data which is present at this location represented by destination. So whatever the operation is, will perform that particular operation on the content of the location defined by the destination, will perform that operation and result will be stored at that second position, because whatever is at the second position with respect to address field will define your destination. So that will be the destination. Now let's look at the question carefully. So what is happening? Now it is saying using X as the stack pointer. So it is actually saying that X is nothing but a stack pointer register. Stack pointer register will define what? At any point of time, stack pointer register will point to the top of the stack. Right? Okay. Now, which of the following instruction can pop the two elements from the stack? So basically, this is the evaluation of the type that, let's say, assume that you have a stack and at some point of time the content A is here and B. So at this point of time, top of the stack is nothing but B. So first you need to pop these two elements, that is you need to pop B, you need to pop A. Then perform the addition operation, and you need to push the result back to the stack. So what's the idea? When you are popping two elements, first it will be popped, top will start pointing to this, you will pop this, top will start pointing to this. Now what you need to do, sir, when top is at this particular location, you need to push this result, that is first you will increment the top and then you will push the result into the stack. Clear? So that's the idea. So basically, let's assume that at some point of time X is pointing to this particular location. Now the opcode is nothing but addition. Very good evening everybody. Very good evening Shubham, Chandrayan, yes, Striver, Sk Music, very good evening. Now let's look at this. Let's look at this particular concept that, okay sir, X is at this point. Now I need to check that which of the following can perform this task, that is pop the second element, pop the first element, then perform the operation and push the result back into the stack. Sir, let's look at this. Sir, what will happen with respect to this? We will pop B because the effective address will be based on the value of X, which is the stack pointer. After that we will decrement. The value, that is after popping this element B, the X will start pointing to this. Now we need the second operand. Second operand will be specified by the second location. So with respect to second location, the effective address is nothing but the content of memory location X. Yes sir, the content of memory location X is nothing but A. Because this time after decrementing the pointer, X is pointing to this location A. Clear? Now we will perform the addition operation, that yes, we will perform A plus B, or basically it will perform B plus A. It's also fine because the addition operation, so it is commutative, so it will eventually perform source, that is the first location content, plus destination, that is the second location content. So content of the first location with respect to my example is B, content of the second location is A, so it will perform B plus A and it will push the result back into the stack. Sir, at which location? Whichever location is being represented by this second operand. At that particular location, I'll push this result. So obviously, after popping this second element, we are not doing anything. Therefore, X will eventually point to this particular location itself, that is A. And at this location will update the result B plus A. Whatever is being represented by the second address, at that particular address will push the result. Clear? Top of the stack is pointing to X. So whatever is being represented by this second field at that will become my destination. Address. Yes sir. So the first one, or the first instruction itself, can perform this task. Now the ambiguity. So let's look at this. We actually need to think about the other options as well. So let's do it. That what is being evaluated by the other operation. So this is A. X is pointing to this. So pass, it will pop the element B. Now, after popping the first element from location X, the value of X is not being changed. Value of X is not being changed. Therefore, after popping this first element B, the X will point to the same location, and for the second operand, you will first pop the second element from that location itself, that is B only, and then you will decrement the address. So, do we need to evaluate B plus B? No, no sir. So, if you use B, if you use option B, then it will evaluate B plus B, which is wrong. So, what happens with this particular situation? So, it will be pre-decrement. It will be pre-decrement. So, what will happen? So, with respect to pre-decrement, if this is the scenario, then this will first decrement the value of X. That is, first we will decrement the value of X. Then we will get the effective address based on the content of location X. So, content of location X is nothing but your A. That's it. So, this is your, this one is fine. That okay sir, operand A is being popped. Now what? Sir, for the second element, what is happening? Sir, after this pre-decrementation, as X has started pointing to this data A. Now, here, this second destination says that the operand will be available from location X itself, and then will increment the value of X. So, if we get the second operand also from the location X, and now the new location X is actually the value of X decremented. So, initially X is pointing to B, and because of this pre-incrementation, X will start pointing to this location A. So, you will get the first operand as A, and the second operand will be nothing but the content of location X. Now, at this point of time, when X is pointing to this location A, content of X will be A only. So, you will perform the operation A plus A, which is wrong. A plus A, which is again wrong. We need to perform the operation either A plus B or B plus A. Clear? Now, so what happens with respect to option D? So, first we will decrement it. So, we will eventually get A. Then here also, so we are eventually getting A only. So, all B, C, D are wrong. All the options B, C and D are wrong. The correct option is option A. Clear? But what will be the output? That's what you need to realize. Let's look at the question number 3. So, this is basically a concept which generally we discuss during the interrupt discussion, that there are 3 different types of interrupt: internal interrupt, external interrupt, and your software interrupt, right? So, please try to understand this. Which of the following must be true from return from exception? Return from exception. So, what do I mean by exception? When we are executing certain instructions which are raising the exception, we are executing certain instruction and they are raising the instruction, then we will try to return from them. And basically, what are these instructions? These are the privileged instruction, and these privileged instructions are nothing but interrupt. These privileged instructions are nothing but interrupt. So when you say return from exception, that is, we are returning from the interrupt. So what type of instruction interrupt is? Sir, interrupt is a privileged instruction. Yes, it will always execute in the kernel mode. Interrupts are the privileged instruction. They will always execute in the kernel mode, right? Trap is a form of interrupt. Trap is a form of interrupt, right? So these two are things that yes sir, it must be a trap instruction, that obviously because of that sir, some exceptions are being raised, so it's a trap instruction, that you are being trapped in something, so you are trying to return from that. Now it must be a privileged instruction. Yes sir, while you are returning from the exception, you are still executing the instruction of that interrupt only, right? So yes, you are still executing the privileged instruction. Now let's look at the third point. An exception cannot be allowed to occur. An exception cannot be allowed to occur during execution of an return from exception instruction. Yes, when you are returning from an interrupt, when you are returning from an interrupt, another interrupt is not allowed to occur. Once you are done with the complete execution of that particular interrupt, then only you will go into the software mode. When you are in the or I would say user mode, when you are in the user mode, then only a new interrupt will arrive, that is a new exception may arrive. So an interrupt cannot be allowed to occur, because what happens if you are returning from an exception and another interrupt occurs, then just after returning from that particular interrupt, you will do what? So when you will return from the interrupt, you will eventually check for the next interrupt and you will start executing the next interrupt. So you will not be able to store the correct state of the CPU if you do not first transfer the control to the original program in which you were when the previous exception occur. Clear? So all three must be true. All three must be true. So that's a deep analysis, but yes, obviously this concept is related to concept of interrupt. When we will discuss the concept of interrupt, we'll discuss all these things in detail. And obviously all of you who have already studied the concept of interrupt, they know that all these three things must be true with respect to return from exception, instruction, execution. So one only, no. Two only, no. One and two only, no. All three must be true. All three must be true. Okay, sir. Let's look at the question number 4. Again, which of the following is are true? So this time, this statement or these questions are in the form of is are. But now we have the possibility of MSQ. So such type of options may not be available. Such type of options may not be available. If the options are available, then you may rule out some of those options if you don't have the complete knowledge about the question. But in the MSQ, I can actually give one more option here, 1, 2, 3, 4, and I may ask you that tell me which one of these 4 are true, right? So in the scenario of MSQ, this type of questions will become more complicated. So please, it's important that you understand the theory of the computer organization and architecture properly, because good number of questions or good number and good quality questions can be framed from the computer organization and architecture when it is it's about MSQ type of questions. Okay, sir. Let's look at this. So which of the following is are true of an auto-increment addressing mode? What is auto-increment addressing mode? That you can actually say that, yeah, that's what we have discussed. So it's a kind of auto-increment. It's a kind of auto-increment that you will get the address from that particular location and you will increment the value of address so that the next content will be available from the next location. So that's the auto-increment addressing mode. Please try to understand. Auto-increment addressing mode has nothing to do with the self-relocatable code. Which particular addressing mode is used to write self-relocatable code? Sir, to write self-relocatable code, we use base register addressing mode. Which register addressing mode? Base register addressing mode. That with respect to base register, we can relocate the code from one location to another location. So yes, this first statement is obviously false. First statement is obviously false. What about second statement? If it is included in an instruction set architecture, means if in your processor you define some type of addressing modes, right, then an additional arithmetical logical unit is required for the effective address calculation. So what does it do? Sir, the auto increment addressing mode will tell you that if it is written as R0 plus, and let's assume that this R0 is providing you the address, then auto increment. So the content of register R0 will give you the effective address, and after evaluating this address, you will increment the value by some size. You will increment the value by some size. Clear? So that's the idea, that okay, if this is the situation, then if we include this type of addressing mode in the instruction set architecture, then it says that an additional ALU is required. No, you are already having an arithmetical logical unit in your processor. So why do you need an extra ALU? If you use an extra ALU, then perhaps you will be able to utilize this addressing mode more efficiently, but it is not necessary. It says that an additional ALU will be required if you use this particular addressing mode. No, it's not necessary. See, you may include an extra arithmetical logical unit in order to make the system more efficient whenever this type of addressing mode is being used, but it is not necessary. You may use your existing ALU for the purpose of this incrementation operation. The only difference is that this time the execution of this particular addressing mode will make the overall execution slower. But I mean, when you say additional ALU is definitely required, no. So may or may not be. So statement 2 is also false. Sir, the amount of increment. So I said that we will eventually increment the value. So the amount of increment depends on the size of data item being accessed. Yes, sir. Please look at this. That there is an address. And this is your address 100. With respect to, and register R0 initially contains the value 100. Let's assume that R0 is pointing to this value 100. So I'll access the content of this register R0, and this content of register R0 is actually nothing but 100. So we'll get our first effective address. After that, we'll increment the value of R0. So if we simply say R0 will be nothing but R0 plus 1, then the next address will become 101. But is it necessary that the next operand will be available at the location 101 itself? No, sir. We know that we will require one word information. And if the word size is of 4 byte, then ultimately the next location at which the next word will be available will be 104. So what we need to add in the existing value or in the existing address? Sir, we need to increment the existing address by the value same as the size of the data which is being accessed. Clear? Therefore, yes, the statement 3 is correct, that if we are using auto increment addressing mode, then every time we will have to increment the value. Every time after accessing or after evaluating the effective address, we will have to increment the value by the size of data that is being accessed. Clear? So yes, which one is correct? Sir, only 3. 3 only. First one is not correct because for the purpose of self-relocatable code, we use the concept of base register addressing. And obviously, this ALU may be used but not essential. Okay, next. Look at the next question. So this is a question which is related to concept of instruction format. Okay. Consider a processor with 64 registers and an instruction set of size 12. What does it mean? Instruction set of size 12. What is an instruction set? If you guys are not aware of this particular term, then perhaps you will not be able to solve this particular question. Sir, what is an instruction set? Set of all the instructions, set of all operations supported by processor. So in the instruction set, you will have all the different types of operation. If the size of this set is 12, means there are 12 different types of operations. If the size of this set is 12, means there are 12 operations or 12 type of instructions, 12 type of operations. So a processor with 64 registers and 12 instructions. Each instruction has 5 distinct fields. Each instruction, I don't know the overall size, but please try to understand this concept. This is your one instruction. And in this instruction, there are 5 fields. 1, 2, 3, 4, 5. Clear? And what are those fields? Namely, opcode. Opcode is used to represent the operation. Sir, there are 12 operations. So, to represent 1 out of 12 operation, how many bits will be required? Sir, to represent 1 out of 12, we require 4 bits. So, using 4 bit, you can represent up to 15. So, up to 12, you can definitely represent using 4-bit opcode. Apart from that, 2 source register identifier means this 2 fields, register field 1 and register field 2. These 2 fields will be used to identify a register on which you need to perform the operation. Sir, how many registers are there in the processor? Sir, there are 64 registers. So, to represent 1 out of those 64 registers, you will require 6 bits. So, each register identifier field will be of 6 bit. Each register identifier bit will be of 6 bit. 1 destination register identifier. So, 2 source, that is okay. So, if you are saying R0 plus R1 and you need to store the result into R2. So, first will represent R0, second register field will represent R1 and the destination, that in which register you want to store the result. So, for that purpose, you will have a third register field and obviously it is also a name of the register. Therefore, this will also be of 6 bit. And apart from that, and a 12-bit immediate value, immediate addressing mode, that is whenever you want to represent a constant in the instruction, then you can eventually use an immediate field in the instruction. So, this is an immediate value and the number of bits for this particular immediate field are 12 bit. Okay. So, these are the only 5 fields in your instruction. So, what is the overall size? 6, 6, 6, 12, sorry, 18, 12, 30, this is 34. So, overall 34 bits are there. Please look at one more thing. Each instruction must be stored in memory in byte aligned fashion. Byte aligned means the instruction must be stored in the byte, in the form of byte only. So, you know, sir, what is the size of this particular instruction? 34 bit. So, if we talk about byte, so sir, how many byte are they? So, they are basically 4 point something. So, for each instruction, how many bytes will be required? So, if this is your instruction 1, and the memory is byte addressable, so you can store 4 bytes of this or 32 bits of this particular instruction into 4 cells, but in the next cell only 2 bits are required. But what will happen with the remaining 6 bit of that particular cell? Sir, waste. The remaining 6 bit will be wasted. You cannot start storing the next instruction from this location itself. Otherwise, the things will become complicated. How will you provide the address of the next instruction? The address will be of this particular cell. You cannot provide the address as the middle of some cell. That okay, you need to go 2 bit ahead from this particular cell. You cannot provide because the next one will be 4 bit ahead, next one will be 6 bit ahead, etc. So therefore, we are storing the instruction in the byte aligned manner or byte aligned fashion. So for each instruction, how many bytes will be required? Sir, 5 bytes will be required for each instruction. Now the question is very simple. If the program has 100 instruction, then the amount of memory in bytes consumed by the program text. We know that we need to store the instruction in the byte aligned fashion. There are 100 instructions. For each instruction will require 5 bytes. Therefore, 500 bytes of space will be needed. Clear? Okay, sir. Let's move to the next question. There is also of the similar type. A processor, and these are the similar type of questions asked in 2016. Both of them are of the same paper, from 2016 only. So please, similar concept, two questions. A processor has 40 distinct instructions. Distinct instructions means type of operations. Basically, that's the one confusion which student will generally have, that they think that instruction, whenever we say instruction, they think of the instruction which are present in your program original high level language, or they may think that, okay, this is one instruction, add R0, R1, R2, and another instruction is add R4, R5, R6. So these are two instructions from your point of view. These are two instructions from your point of view, but from the CPU point of view, both of them are addition instruction. So CPU, whenever we are talking about type of instruction with respect to CPU, then we are talking about the operation, that what operation is being performed. On what operands it is being performed is not relevant. On what operand that particular operation is being performed is not relevant. We are eventually concerned with the type of operation that we are performing, because the CPU need to learn what? That how to perform the addition, how to perform the subtraction, how to perform the multiplication. That's what the processor designer need to teach this control unit. The processor designer, once it has taught the control unit that how to execute the instruction add R0, R1, R2, then the control unit already know that how to execute the instruction add R5, R7, R9, because the procedure is same. So how to execute the addition operation, that's what we need to explain. Clear? So that's the one thing, that whenever you see instruction, in general, in some other subjects, the instruction may be the programming statement written by you, but for computer organization and architecture, instruction is the type of operation. Now, our processor has 40 distinct instruction, and how many registers? 24 general purpose registers. Right. Now, a 32-bit instruction word. So obviously instruction size is same as word size. So a 32-bit instruction word, that is one word instruction, has an opcode, okay, in the instruction. So this time it is specifying the bits in the or the field in the instruction in a different format. That in the instruction, what will be present? So in the instruction you will have opcode, okay, a 32-bit instruction. So the size of this instruction is 32-bit, has an opcode, 2 register operands. So register field 1, register field 2, 2 register operands, and an immediate operand, and one field is definitely for immediate operand. Now it is asking the number of bits available for the immediate operand field. So it is asking that how many bits will be available for this immediate operand. The question is quite simple. Why? Because there are 40 distinct operations. So to identify one out of those 40 operations, how many bits will be required? So to identify one out of 40 operations, 6 bits will be required, and there are 24 general purpose registers. To identify one out of those 24, you will require 5 bits. So 5 bit for this and 5 bit for this. Both are the register fields, so you will require 5 bits. So 5, 5, 10 and 6, 16. So 16 bits are gone out of 32 bit. How many bits are left? Sir, 16 bits are left for immediate operand field. How many bits? 16 bits are left for immediate operand field. Clear? So these two questions are related to the concept of instruction format. Okay, sir. Next, this is the very basic question of microprogramming, or basically control unit design. Horizontal microprogramming. What happens in the horizontal microprogramming? In the horizontal microprogramming, the format of control word. Why do we call it control word? Because these words are stored in the control memory. This is a control word, right? So what are the different fields available? Sir, we have certain fields for flags. We have certain fields for branch condition. These are the optional field. They may or may not be present in a micro instruction. This is control word or micro instruction is the same thing. Why micro instruction? Because being executed, it's available in a control memory which is used to store the micro instruction. So these are the instructions which are being stored, therefore micro instructions. Okay, apart from that, there will be two more fields. One is the address field, which is specify the address of the next micro instruction. Specify the address of the next micro instruction, and one is the control field. Control field is used to specify the control signal. Anybody who knows the concept will directly know the answer of this particular question. Now, what happens to specify control signal? In horizontal microprogramming, control signals are represented in a decoded format. Decoded format means if there are 10 control signals, used within the CPU, then for each control signal there will be 1 bit in the control field. There will be 1 bit in the control field, right? So all the control signals which needs to be generated for this for the execution of this micro instruction, those bits will be 1, and the control signals which are not required for the execution of this particular micro instruction, the bits corresponding to those control signals will be 0, right? So let's assume that this is nothing but signal S0, this is nothing but signal S1, signal S2, signal S3, signal S4, etc., right? So here it says that please try to understand, because the control signals are available in the decoded format, therefore once you have the micro instruction in front of you, you will not have to decode this field to get the control signal. Just by looking at this field, you will be able to say that what are the different control signals which needs to be generated. So you'll know control signal S1 needs to be generated, control signal S4 needs to be generated, and control signal S7 needs to be generated. Clear? So these are the 3 control signals which needs to be generated, and it is directly available in the instruction. So it does not require the use of signal decoders, that we do not need to use the decoder to identify the control signal. Yes sir, this one is correct. Apart from that, sir, one more is vertical microprogramming. What happens in the vertical microprogramming? In vertical microprogramming, if there are 10 control signals, then to identify 1 out of 10, log of 10 base 2, ceiling function of log of 10 base 2 bits will be used. So basically log of 10 base 2 will be nothing but 4. Log of 10 base 2 will be nothing but 4. So 4 bits will be used to identify 1 out of 10 signal. Here for 10 control signals, 10 bits will be used. Remaining field will be of exactly same size. Therefore, you can actually see if this 3 fields are of same size in horizontal and vertical, and the number of bits in the control field are more with respect to horizontal and less with respect to vertical, then the overall control word size will be more with respect to horizontal microprogramming. So it results in larger size micro instructions, that is control word, same thing. It results in larger size micro instruction compared to vertical microprogramming. Yes sir, this one is also true. Now the next one, uses 1 bit for each control signal. That's what I said. If there are 10 control signals, then with respect to each control signal, there will be 1 bit. And that's why we say that it uses in decoded format. Therefore, we don't use the decoder. So the third statement is also true. So all 3 statements are true. So the perfect answer will be option 3. Perfect answer will be option 3. I can provide you with one more option and I can make the question as MSQ. I can provide with one more option and the question becomes MSQ type of question. Next question. Okay, very good question. Very good question. So there are certain things which you need to understand to solve this question. Consider a CPU where all the instructions, look at this, all the instructions require what? 7 clock cycles to complete the execution. 7 clock cycles to complete the execution. Please, this is a question of control unit design, but the information that how many micro instructions will be required for the execution of each instruction is defined in a different format. How? Sir, in general what happens? For the execution of one micro instruction, 1 clock cycle is required. For the execution of one micro instruction, 1 clock cycle is required. Here it is saying that for the execution of one instruction, every instruction for the execution, where all the instruction, that is for the execution of each instruction, we require 7 clock cycles. When we say that 7 clock cycles are required for the execution of each instruction, that is for the execution of each instruction, 7 micro instructions needs to be executed. This is the core of this particular question. This understanding is very important, that there is a CPU, it has certain number of instructions, but the idea is that for the execution of each instruction, you require 7 clock cycles. If you require 7 clock cycles for each instruction, it means that for each instruction, there are 7 micro instructions and each one of those micro instructions will require 1 clock cycle. Therefore, 7 micro instructions will require 7 clock cycles. Hence, the execution of each instruction is requiring 7 clock cycles. That's the logic. Clear? Now, to complete the execution. So, each instruction execution can be completed by the execution of this 7 micro instructions. Now, it is saying there are 140 instructions. So what do we know? 140 instructions each with 7 micro instruction. Therefore, total number of micro instruction in control memory. Why do we use the control memory? Control memory is used to store the control memory is used to store the microprogram, each with 7 instruction in the microprogram. हर इंस्ट्रक्शन के एग्जीक्यूशन का एक माइक्रो प्रोग्राम होता है. इफ यू वांट टू एग्जीक्यूट वन एडिशन इंस्ट्रक्शन, then for the execution of an addition there will be a microprogram which will eventually perform the execution of addition. For subtraction there will be another microprogram. For multiplication there will be another microprogram. Here it is being said that for each type of instruction the microprogram consists of exactly 7 micro instructions. Right? So because there are 140 instructions, there will be 140 microprogram. 140 instructions, therefore there will be 140 microprogram in the control memory. Now 140 microprogram, each with 7 micro instruction, each with 7 micro instructions. So total number of micro instruction in the control memory will be 140 microprograms, each with 7 micro instruction. So whatever this is, 7, 980. Total number of micro instructions in the control memory will be 980. Clear? Very good. Okay, sir. Then what does it say? It is found that 125 control signals are needed to be generated by the control unit. That is, for the functioning of that particular computer, for the functioning of that particular computer, overall need of control signal is 125. Overall need of control signal is of 125. That is 125 control signals are needed. Out of those 125 control signals, some of the control signals will be enabled, some of the control signals will be disabled for the execution of one micro instruction. So what all the control signals will be enabled, what all are the control signals which will be disabled, will depend on the individual micro instruction. Now what are so okay, so this is known that 125 control signals are needed or for the execution by the control unit. Now while designing, what type of control unit? While designing horizontal microprogrammed control unit, horizontal microprogrammed control unit, just now I have explained the format of control word or micro instruction. Just now I have explained the format of control word and micro instruction. So what is the format? Please, you will get this. This is your micro instruction. So what are all the fields? Those are available. Sir, one is the flag, branch, decoded control field, decoded. If you are using or if you are designing horizontal microprogrammed control unit, then the control field will be in the decoded format, and one is the address of next micro instruction. Address of next micro instruction. Now let's look at this. Okay, control word. Single address field format is used. Single, look at this. This is another term which can confuse most of the students. Single address field format is used for branch control logic. Single address. What does it say? When you will go in the detail of this particular concept, you will realize that there are two different types of format. One is single address field format, another is two address field format. In the single address field format, what will happen? Sir, whenever the branch condition is true, and the branch needs to be taken, then this address field will provide the address of the next micro instruction. And if the branch condition is false, then you don't need to use this address field present in the micro instruction. You will eventually increment the content of micro instruction register. Let's assume that this is a micro instruction which is available at location 105, right? So the next micro instruction will eventually be available at location 106 in the control memory. If this particular micro instruction is present at location 105, then the microprogram, what are we storing in the control memory? Sir, we are storing the microprogram in the control memory. Therefore, all those 7 micro instructions of the microprogram will be in a sequence. We need to execute those micro instructions one by one. So if the condition is true, then only we will have to jump randomly from one micro instruction to some other micro instruction. Otherwise, the execution of micro instruction will take place in a sequence. So if the condition is true, then only one address field is sufficient to represent that at which particular address from which particular address you need to execute the next micro instruction. If the branch condition is false, then you don't need to use this address. You can simply increment the address of the current micro instruction to get the address of the next micro instruction. So this is the single address field. One more is two address field format. In two address field format, we'll have two different address fields. One address field will specify the address of the next micro instruction when the condition is true, and next another address field will specify the address of the next micro instruction when the condition is false. But we don't actually need the extra field for the false condition, because we can simply increment the current value of the address to get the address of the next micro instruction. Therefore, this to address field format is not used. To address field format is not used. It's just a concept. So that's okay. That this is the format. That's what that's the same format which we just discussed a minute ago. Now, what is the minimum? So it is asking, what is the minimum size? What is the minimum size of the control word? What is the minimum size of the control word and control address register? Hello. What is the minimum size of the control word and control address register? Minimum size. What did I just say? Sir, you just told us that these two fields are optional. They may or may not be present. They may or may not be present in each control word. But these two fields are mandatory. These two fields, that is control field and address field, are mandatory. Clear? Now please try to understand this. That's because it is a horizontal microprogram control unit, therefore control field will be of exactly same size as the number of control signals. Will be of same size as the number of control signals. So because there are 125 control signals, for each control signal 1 bit will be required, therefore 125 bit will be required in the address field, and overall there are 980 micro instructions. So the size of control memory is 980 micro instruction. To identify 1 out of 980, how many bits will be required? Sir, 10 bits. To identify, oh sorry, not here, this is not a field. To identify 1 out of 980 instruction, how many bits will be required? Sir, 980 bits will be required. To identify 1 out of 980 instruction, 10 bits will be required. 980 log of 980 base 2. Sir, so these two fields will formulate your control word. These two fields, up to this only. These two fields will formulate your control word. This is an extra bit. So this two field will formulate the control word. So what is the size of this control word? 125 bits for control field, 10 bits for address field. Therefore, the size of control word is guaranteed to be, minimum size of control word is guaranteed to be of 135 bits. And what is the control address register? Sir, memory address register is used to access a memory cell. Similarly, control address register is used to access a control memory cell. So how many cells are there? Sir, 980 cells are there. To fetch 1 out of 980 cells, or to represent 1 out of 980 cells, control register must be of 10 bits. Control register must be of 10 bits. Exactly same as the size of address field. It will be exactly same as the size of address field. So 135 and 10, that is correct answer is option D. Correct answer is option D. That will be all. Now you will have a session on the concept of Python, right? So go attend that particular session. Tomorrow we'll discuss the remaining questions of GATE 2002, 2008 and 2016 of computer organization and architecture. That will be all for this particular session. Thank you very much. Take care. Keep learning.